Welcome to Ask and Learn.
In part A of this problem, we are told that N2O5 and F2 react to form NF3 and O2 in a gas phase reaction. Since we know that these are gases, all of the substances will be in that state. So we can set up the reaction in this way based on the information that we're given in the problem statement. And in part A, we just have to balance this reaction. So if we look, we can see that we need 2 moles of N2O5 in order to balance 4 moles of NF3 to get 4 nitrogens on each side of this reaction. After we do that, we have 10 moles of oxygen atoms on the left side from N2O5, and so we need a coefficient of 5 here to balance out those 10 oxygen atoms. And we also see that on the product side, we have a total of 12 fluorine atoms from 4 moles of NF3. And so we need a stoichiometric coefficient of 6 for F2 in order to balance those out. So that is the answer to part A, as we have successfully balanced this gas phase reaction. Part B, we want to determine the change in Gibbs free energy of this reaction. This is the equation that we use in order to find that, where we first calculate the change in Gibbs free energy of the products and then subtract the total change in Gibbs free energy of the reactants. So we can break up the terms for the products and reactants. And starting with the products, when we examine the equation that we just balanced, we see that on the product side we have NF3 and O2. Remember that just like for changes in enthalpy, delta H, delta G, change in Gibbs free energy, is similar in that the change in energy resulting in the formation of naturally occurring elements in their natural states is 0. And that is the case for diatomic gases like F2 and O2. So we do not account for those species in our equation, and so the only product of interest for us is the 4 moles of NF3. So we have 4 moles of NF3, and we can look up in the appendix what the change in Gibbs free energy of formation at standard conditions is for that chemical species, and when we multiply those values together, cancel off units of moles, we are left with total Gibbs free energy change units of kilojoules. And then for the reactants, again, since F2 is naturally occurring, we ignore it and only examine the 2 moles of N2O5. 2 moles of N2O5 multiplied by its respective value for the change in Gibbs free energy of formation at standard conditions gives us the total Gibbs free energy change of the reactants. And then we take the total Gibbs free energy change of the products minus the total Gibbs free energy change of the reactants. And when we do that, we get a final answer for delta G of reaction to be negative 569 kilojoules. And that is our final answer for part B. And again, this is delta G of reaction at standard conditions, denoted by this symbol. In part C, we want to use that value that we just calculated in order to find the change in Gibbs free energy at new reaction conditions. So this is the equation that we use in order to do that. And we are told the temperature, and we know R is a constant. We just solve for the change in Gibbs free energy of the reaction at standard conditions. So all we need to find is Q, the reaction quotient. And we can write out Q in terms of the given partial pressures in part C by doing the partial pressure of the products raised to the power of their stoichiometric coefficients, and then multiply that value for each one of the products for all the products of this reaction, and then divide that same quantity for the reactants. So when we do that, our expression for Q should look like this, where we have the partial pressure of NF3 raised to the power of 4 times the partial pressure of O2 raised to the power of 5, since those are the products of this reaction with their proper stoichiometric coefficients. Then we divide that by the partial pressure of N2O5 squared times the partial pressure of F2 to the power of 6, which is what we can see on the denominator of our expression for Q. We are given values for the partial pressures of each one of these species, and so we can plug in what we know into this expression to solve for Q. So 0.25 atmospheres for NF3 raised to the 4th power multiplied by 0.50 atmospheres for O2 raised to the power of 5. Then we divide that by 0.20 atmospheres for N2O5 raised to its stoichiometric coefficient of 2. Finally, 0.20 atmospheres for F2 raised to its stoichiometric coefficient of 6. When we calculate out that ratio, we should get about 47.68, and that is going to be unitless. Now we have a value for Q to plug into this equation to solve for delta G of reaction under these partial pressure conditions. So delta G of reaction equals delta G of reaction at standard conditions, which is what we solved for in part B. And again, that was negative 569 kilojoules per mole. Then we add RT ln of Q. So R is a constant of 8.314 joules per mole times Kelvin. And we are going to want to divide that by 1,000 so that we can get it in units of kilojoules. So times 10 to the negative third kilojoules per mole times Kelvin times the temperature of 298 Kelvin times the natural log of that reaction quotient that we just found to be 47.68. And again, when we cancel off units of Kelvin, this is temperature in Kelvin, we are left with units of kilojoules per mole for delta G of reaction. When we plug that all in, we should get a final answer for delta G of reaction to come out to a value of negative 5.60 times 10 squared kilojoules per mole. And that should be our final answer for part C.